It's nice to be here again. And I'll talk about two different topics. One is unfinished paper with Nicolai, Royban, and Yamada about n greater than 4 supergravities. And it is significantly using the results of also recent paper with Friedman, Van Prooyen, and Yamada. And it is very formal. It will be interesting to people knowledgeable in M theory, string theory, and supergravity. Whereas it turns out to be nicely connected to cosmological studies, which I did in parallel with Ferrara, Linde, Rost, Rase, Yamada, on alpha attractor models, which Andrei described in the talk today. And there will be targets for primordial gravitational waves, which come equivalently, whether I start with M theory, string theory, or maximal supergravity. As long as I start with maximal amount of supersymmetries and reduce it to minimal amount, that will be the target. The models are simple and falsifiable. That's their advantage. So there will be some very formal discussion based on recent computation, but there will be also a justification of the targets. Steve Hawking, in the early days, was very much interested in both topics, cosmology and superspace and supergravity. And that influenced many people, I think, in this room and in the world. So, in short, I'll describe the recent progress in UV properties of perturbative maximal n equals 8 supergravity based on universality of n greater than 4 supergravities, which was recently recognized in our group. And then I'll talk about Planck and future satellite CMB missions. In particular, we will see that the targets will be between what is known to be the target of ground-based experiments, 10 to the minus 2, up to 10 to the minus 3. So let's look what Steve Hawking was telling us in 1980 in his inaugural lecture. He said, at the moment, n equals 8 supergravity is the only candidate for insight. There are likely to be a number of crucial calculations within the next few years which have the possibilities of showing that the theory is no good. Indeed. Immediately, there was a 3-loop candidate counterterm found, but it was not clear whether the 3-loop UV divergence will show up or not. So then Steve said, if the theory survives this test, it will probably be some years more before we develop computational methods that will enable us to make predictions. And before I move any further, some of you may know that there is a strong activity in something called amplitudes. If not for amplitudes, I would have nothing to say here today. So then in 2007, precisely using double copy method with product of two Young-Mills series, they performed calculations. They found the 3-loop counterterm actually vanishes. And then Steve was saying that there will be outstanding problems for theoretical physicists in the next 20 years or so. And this was in 80. So we are much later now. So this formal part of my talk will be, is n equals 8 supergravity perturbatively all-loop finite? What do we know 37 years later now? And I'll tell you as much as we know. So this is a story of recent progress in scattering amplitudes on one side. And this is a story of Planck. And we have seen these pictures in the earlier talk. So those yellow, those two yellow curves are alpha attractor models. And some of you who know me very well, you know I'm a totally formal person. Suddenly I open Planck, and here are those two yellow lines of our model discovered a few years earlier. That was quite gratifying. And so the current situation is the following. There's something called CMBS4 science book, and I was in recent collaboration present. And one of their goals is to study primordial gravity waves, and they plan to go all the way to 2030. And so the models described in my work with Ferrara and Linde and Rase and Yamada and Rost They will present well-motivated new models which originate from string theory, M theory, and maximal supergravity. And the new target have the following nature. So this is their book for future measurements. What you see here as a gray stripe is alpha attractors. And what you see also, what was known at the time when they presented the book last fall, one target, well known, is Higgs inflation, and the other is Tarabinsky. And they were kind of lonely 2 points between ground-based and space-based missions. So from here till 10 to the minus 2, this is where ground-based experiments most likely will go, maybe more, maybe less, depending. And those are future B-mode satellite missions. And there were just 2 targets. And one of the targets here, Higgs or R squared, they depend on number of e-folding. But approximately, they're giving 3 times 10 to the minus 3. Whereas in my evaluation, that the lowest target is 3 times below. It is exactly 10 to the minus 3. And then people who write proposals ask me, maybe I'm wrong in this factor 1 over 3, because it will cost them some number of hundreds of millions of dollars. So I check my computation, and I insist that this is the 1 over 3 is the correct number. And in fact, I'll try to explain why. Why it follows from maximal supersymmetry. M theory, string theory, maximal supergravity. So this is the approximate picture. Everything here is ruled out by the data. This is a logarithmic scale of R and tilt of the spectrum. And so the new targets, there are 7 of them. And here they go. So they are associated with R squared of this Escher disk, which is discrete and goes from 7 up to 1. And as we already have heard, people who do ground-based experiment, they hope to touch the largest one, the number 7, and I'll show you the model which allows the dynamical realization of this target. And people who write their proposals for space mission, they prefer this one because this is a better target. It's way below. Now, the targets are all coming from the fact that E77, the simplest explanation is to follow n equals 8 supergravity. And it has this hidden symmetry, which is known as E77. And according to Duff and Ferrara, it consists of 7 Poincare disks. So what is maximal n equals 8 supergravity? The theory has one helicity, one negative helicity graviton, one positive. It has 8 gravitinous negative and positive helicity, 28 vectors, 56 spin 1/2, and 70 scalars. So the old wisdom, and some people are in the room, was that because we can construct on-shell superspace, and we can construct tensor calculus, and therefore all higher derivative terms are possible. And that would predict that the divergences would start with 8 loop level, but linearized would start with 3 loop level. For example, we can use a superspace torsion, and then the expectation was, because there is tensor calculus, it means infinite proliferation of candidate counter terms. Where they start is not of major importance, because if they proliferate anyway, it doesn't matter. On the other hand, for our understanding of what we know and what we don't know, also because the computations are limited to low-level loop, it's good to know where they start. And there was a significant progress, computational progress in this field. So as I told you, E77, on one hand, is the hidden symmetry, which explains certain absence of UV divergences already, and everybody agrees on this up to a certain level. On the other hand, it is E77, which has 7 disks, which predicts those B-mode targets. So after the old wisdom, let me switch to new era, new people, new computers, new rules. Never use supergravity. Build it from Young Mills. This is what amplitude people do when they compute things. So they found in explicit computation that there are no UV divergences in 3 and 4 loops. At 5 loops, and this is the latest I asked them to do, so as of a couple of days ago, after many years of effort, Byrne et al. Have figured out a new double copy method that allowed them to construct n equals 8 supergravity 5-loop 4-point integrand. They are currently integrating in dimension 24 over 5, and you may have heard from Michael Green how crucial this computation will be, to see if it behaves the same way as Young Mills or not. And not clear how long this will take. Could be tomorrow or a while from now. So what is the explanation of these facts? First of all, when I have heard that they found absence of UV divergences at 3 and 4 loop, I have constructed light con superspace counterterms. I was trying, and Lars Brink, who is here, just confirmed to me that he also tried, and we both agree that they're not available as today. And this would predict UV finiteness. And this was done back in 2008. And despite the attempts, we have not able to produce the counterterms. So they're basically still not available, which is an easy explanation of things which have been computed. However, people are not happy with light con superspace. And between 3-loop and 6-loop finiteness, Brodel and Dixon, Bysert, Elwang, Friedman, Kiermaier, Morales, Stieberger, Basar, Howe, Stella, they produced arguments following from this hidden symmetry, which is E77. And Bjorsen and Green suggested that string theory indicates that maybe starting with 7-loop, there will be a UV divergence, but this we don't know yet. So the way people studied E77 was to look at soft scalar limit. This is so-called Adler's zero. And this soft scalar analysis, starting with L equals 7, is inconclusive because the amplitude has so many momenta in higher loops, and therefore soft limit is simply not useful anymore. So this was the reason why they stopped at explaining after 7-loop. But E7 symmetry also acts on vectors, and this requires current conservation. This is why it is hidden, this is why it is subtle, and this is what was happening. So my question was, if everybody trusts continuous global E77 at from 3 to 6 loops, what is the prediction at higher loop? So I revisited the story back in 2011, and I noticed that something which is known as Netter-Gaillard-Zumina current conservation is inconsistent with E77 of the candidate counterterm. It should not be invariant. Then Basar and Nicolai came with a statement that yes, Netter-Gaillard-Zumina current conservation is inconsistent with E77 invariance. However, there is a procedure of deformation of the linear twisted self-duality constraint, which should be able to fix the problem. And then with Carrasco and Royban, we revisited this statement, we confirmed it, and we found that there exists a modification which will explain some relatively simple model, but of course not maximal supergravity. At this point, I thought I will never ever go back again and study this model. However, in summer of 2016, I happened to be at Melbourne at SUSY 2016, and also Herman Nicolai was there at the same time, and he suggested, let us revisit this story, which we did. So a year ago, we started this story, and I hope to present the result. So what is special about hidden symmetry? The duality doublet consists, first of all, of the Maxwell field, d mu a nu, but also it consists of the derivative of the action over f mu nu. And therefore, it significantly depends on what kind of action you have. So under this symmetry, there is a transformation of the doublet like that. And so to provide the symmetry, it is necessary that the action transforms in a specific way. It should not be invariant. What the symmetry does, it flips field equations into Bianchi identities. So this is a sophisticated symmetry. And just requiring the Lagrangian to be invariant is not correct. So the new story started in 2014 when Byrne, Davis, and Denon have computed n equals 5 supergravity and found that it is UV finite at 4 loops. And for 3 years, there was no explanation whatsoever. So step 1 was, in my paper with Friedman, Van Proyen, and Yamada, we have shown that there are no anomalies at one-loop amplitudes in all these supergravities. It was also known that in n equals 4, there are anomalies. And moreover, those anomalies have shown up in the computation of the 4-loop UV divergences. However, the absence of one-loop anomalies agrees with UV finiteness of 4-loop in n equals 5. So this is where something which we started with Andy Strominger, I don't know if he's here. We started studying black holes, and we noticed with Ferrara soon after that there is something called universality of black hole attractors. And in particular, they're always described by something known as a coset space. And to make it short, whatever E7 does for n equals 8, SO12 does for n equals 6, and SU15 does for n equals 5. The reason this universality was so important, because the computations are known in n equals 5, but we want to know what is happening in the maximal case. And because the formalism works for all of them simultaneously, that was a great advantage. Moreover, it was known in mathematical literature by Brown, and then Duff et al. And Ferrara and myself introduced it with these name groups of type E7. So whatever is E77 or SU15, they have the same features. And therefore, whatever they computed in n equals 5, we can relate to the maximal case. OK, so now E77 is generalized to E7 invariant. And for example, in n equals 5 case, where the computations are available, duality symmetry, the same hidden symmetry, is SU1,5. So now I'll start presenting result of this unpublished paper. And because it is somewhat significant what exactly we can say, Radu Roiban visited me at Stanford, and I just visited Herman Nickel in Potsdam to agree about what we want to say. Our strategy is to find the reason why those UV divergences for n equals greater than 4 are absent. And the story goes that in 2011, Bossard, Stelle, Hove, and Van Hoff, sorry for omission, predicted that there is a family of counterterms. One for, they're always for the number of loop which one less than number of supersymmetries. So they predicted that for n equals 4, L equals 3, 5, 4, and 8, 7, there will be UV divergence. But the computations have been performed. Here, they were found finite, finite, and here we don't know. So that is the story. Now, n equals 4 is compromised because it has anomaly. And so we don't trust quantum theories which have anomalies. But n equals 5 does not have anomalies. So why it is UV finite, despite the existence of this legitimate counterterm? It looks like that. My purpose of showing you that it just depends on n. So any n is served by this candidate into UV divergence. And they have not found it. And the reason, as I told you, that E7 invariance breaks Netter-Gaillard-Zemina current conservation, and therefore the action has to be deformed according to Nicolai and Bussard to restore duality symmetry. So to summarize the situation, our explanation of why they found it is like 82 for-loop diagrams. It is a huge amplitude computation. They compute the on-shell S matrix. And it's just incredible how many terms had to cancel. And for those of you who know how it works, so there are terms 1 over epsilon 4, which just signify that the UV, that subdivergences cancel. There are 1 over epsilon cubed, 1 over epsilon squared. They all cancel, and this is just a check that the computation have been done right. But 1 over epsilon, the true UV logarithmic divergence, also canceled. And so for 3 years, no explanation whatsoever. So our explanation now comes that it is this duality current conservation which requires the action not to be invariant, but to transform in a specific way, can be analyzed. And this is what we did. So this is new. And so we have constructed the complete supergravity for any n starting with 5. And this is a bosonic action, and it has duality current conservation. And so once you add the UV divergence, you have to add infinite number of derivatives to support the current conservation, which is what we did. And the answer was surprisingly simple. So if you then add to the classical theory the first UV divergence, and then you add all the required higher order terms, you can prove that this action has current conservation. And this is the answer. It's really simple. What you see, this is the lambda, the independent new coupling. And because there are inverse power of this operator, there are all higher derivatives. And so in addition to the classical action, there is a UV divergence and all higher derivative terms, and they just fit into one line. And if you take lambda equals 0, it is a classical action. So what we found, surprisingly, that this action has no supersymmetric embedding. So what does it mean? If we didn't make an error, and we believe we didn't, it means that either you have current conservation or you have supersymmetry, but not both. So what we found that SUN symmetry, which provides supersymmetric embedding, is actually on shell broken down to SON, which is not good enough. And so there is a contradiction, 10 minutes, very good, between two requirements of symmetries about which we know that both are not anomalous. So this is the computation of the 6-point amplitude. And we went back and forth, and there was, do they cancel or not? And so all of us on the West Coast, after half a year, agreed they do not cancel. And then I came to Potsdam a few days ago, and Nicolai was saying, I don't believe you. And then after he understood what exactly the procedure was, he came and he told, yes, I agree. So our current statement is that once you take into account the subtlety of hidden symmetry, which requires that in the end of the day, with all higher derivatives, there is a feature that Bianchi identity are flipped into equation of motion. Then this symmetry is implemented in the new theory. Once you have done it, you find that SUN is broken to SON. And this means that this bosonic, what you see here are two 2 vectors and 4 gravitons. And if you look at the expression, it breaks SUN to SON, which cannot happen. It cannot be part of supersymmetric amplitude. We thought for many years that even if we will construct this action with infinite number of derivatives, we will never be able to produce all supersymmetric completion because it will be too complicated. And we will always stay unresolved. But what actually happens when you add amplitudes? They don't care about the action at all. They just compute amplitudes. But the amplitudes must have had this SUN symmetry and not SON. So it is either supersymmetry or E7 current conservation. So, and here is the caveat. On one hand, our new result provides the first explanation of n equals 5, L equals 4 UV finiteness. On the other hand, it appears to be very strong because, as we know, and you may have heard from Michael Green, if you want to go to higher loop, and this is a 4-point amplitude, which is our first source of deformation, you just have to insert a function of Mandelstam variables which depend on ST and U, and you increase your power. And because the internal SON, SUN don't talk to dependence on ST or U, this is a simple procedure. But before taking this line of argument seriously, in view of its importance, because I told you, the result is valid for any n, in particular for n equals 8. Doesn't care on the number of the loop. It is the first explanation of what happened in n equals 5 case. Then it becomes a prediction for maximal supergravity that it is finite at all loops, and we don't want to take it seriously. So we try to find an error or a different philosophy. And so we decided to consider this deformation where the lambda parameter depends on gravitational constant. And so what we did, we discussed the situation where the original lambda depends on 1 over epsilon, which is a logarithmic divergence, and kappa to the power 2L. And the next will be lambda squared, which will be kappa to the 4L divided by epsilon squared. And then we did a very extensive search. We tried to find intermediate loop amplitude divergences, which would restore SUN and supersymmetry broken by a UV divergence. If we would find a restoration of supersymmetry, it would indicate that our approach with independent parameter of deformation need to be reconsidered. But so far, we did not find the restoration of SUN, and there is no indication that there is a loophole in our previous argument. So let me try to summarize where we are. We have computed the on-shell bosonic amplitudes which result from the deformed action with E7 duality current conservation. And the deformation parameter is independent of gravitational coupling. And we found that in this approach, the on-shell bosonic amplitudes inevitably break SUN to SON. Such amplitudes do not have a supersymmetric embedding. And if E7 symmetry and supersymmetry have no anomalies, which we have all reason to believe, the only way to validate both of them is to have UV finiteness. Only in such case, there is no need for deformation with higher derivative terms. So the absence of UV divergence in case which has been computed just tells us there was no reason to have anomalies, and therefore, to protect both symmetries, we have UV divergence. So N5 for loop is experimental point supporting this picture which predicts UV finiteness. And no other explanation is available. The argument appears to be valid for any loop for n greater than 4, but there is this issue of kappa-dependent lambda, which we plan to study more. So E7 symmetry protects it together with maximal supersymmetry from UV divergences, at least up till 7 loops, and everybody agrees on this. In cosmological setting, the models with maximal supersymmetry, consistently truncated to minimal, are based on the same symmetry. The same E77, I'll show you the targets for the B mode. That is the story. You may see here that the size of the triangles here and at the boundary is the same. And this was noticed by Duff and Ferrara. There is a subgroup with 7 Poincare disks, and each disk has a size alpha equals 1,3. At the cosmological setting, Higgs inflation and Starobinsky model correspond to alpha equals 1, which is the reason for 1/3, which, as I told you, almost a joke, will cost hundreds of millions of dollars. So we recently produced some interesting models, which I probably have no time to describe, but let me still try. So based on these Poincare disks, in general, we can easily construct supersymmetric models which have this phi divided by square root of 3 alpha, which is the size of this disk. And the size is 3 alpha. So the models have very simple geometric meaning. There are certain other features which correspond to adding anti-D3 brane on the string theory side. But the most important observation, we call this new class of model cosmological model building paradise, because they easily allow us to build things and establish stabilization of unwanted modula, which I'll skip again, have to do with tessellation of the disk. Here is 3 alpha equals 7 example. This is 10 to the minus 2. The target, which will work for maybe ground-based experiment, maybe beginning of satellite experiments. So there is something called Keller function. If I know Keller function, I can compute everything. We start with 7 disks. We do this procedure of merger, which Andrei Linde partially described. And we can compute easily masses of every other field, except the inflaton. And we end up, during inflation, the potential is a cosmological constant plus tanh squared, and phi is divided by square root of 14, the model have de Sitter exit from inflation, and the prediction is 10 to the minus 2. However, if instead we arrange the model slightly different, it will give us 3 alpha equals 1 example, which is way below. And then it is slightly different configuration in the Keller function, and everything follows. And there is a dependence between the geometry and the potential, which is built into this new construction. As a result, this model of one disk has, again, the cosmological constant, which corresponds to the Sitter exit, and it gives tanh squared divided by square root of 2. And this is a model which has approximately 10 to the minus 3 prediction. All of these models are sitting in the correct place for the value of spectral index, and therefore they are quite useful. And they are sitting and waiting for where the B modes will be discovered. And I'm precisely about to finish. So the corresponding satellite proposal now have beyond Higgs inflation and Starobinsky in the regime between 10 to the minus 2 and 10 to the minus 3, at least 7 new targets, each of which has a very simple justification from models of maximal supersymmetry, M theory, string theory, maximal supergravity, and they're falsifiable. So there is a lot of effort going into these models, and it is precisely after ground-based experiments that we may infer some information here. So Steve Hawking, the optimist, in 80, he told there will be outstanding problems for theoretical physics in the next 20 years or so, with regard to maximal supergravity. Now in 2017, maybe we have started nailing it down. Thank you.
Thank you very much. We're a bit behind schedule, but are there any quick questions?
Renata, you were using these duality symmetries, supposing them to be valid as continuous.
Yes.
I mean, yeah.
Right.
Whereas don't we know they're broken down to discrete subgroups?
Perfect question. Perfect question.
But you have the perfect answer, right?
I do, yes. So I had this slide that the only known explanation as to why 3-loop, 4-loop, 5-loop, and 6-loop in n=8 supergravity are finite is based on continuous U77. So whoever else will tell me they should be broken to discrete, I'll tell them, okay, give me the better explanation of computation that those loops are finite. There is no other explanation. So you have to consider the fact that they're broken because they're broken to discrete. On the other hand, soft limits require continuous symmetry, and they provide the explanation. So once you take this into account, you ask yourself, how are they broken? How do I know?
Another?
Aren't you just saying there that, so we shouldn't believe the arguments that you were presenting unless we already knew that the answer was correct?
Well, I would say, looking back, because they discovered the absence of UV infinities back in 2007, 10 years later, it remains the only explanation. It is a continuous U77, which explains huge computations. And there is no other argument. I think it's time to ask, when we look at the sky, what we learn there, and we compare with whatever we do.
Okay, well, let's thank you very much. Let's thank Renata again.